Welcome back to the Explainer. Today, we're basically firing up a futuristic heads-up display to run a deep scan of reality itself. We are going on a seriously incredible journey. We're going to start from the fundamental equations that govern the entire universe, zoom all the way down into the quantum atomic engines that power your everyday fridge magnets, and then pull all the way back out to view the Earth itself as one giant magnetic shield. So, here are the system scans we're running today. 1. The blueprint of electromagnetism. 2. The displacement current bridge. 3. The quantum magnetism engine. 4. Classifying magnetic materials. 5. Domains and hysteresis. And finally, 6. Earth as the giant dipole. All right, let's kick things off with Section 1, the blueprint of electromagnetism, Gauss's law for magnetic fields. Look closely at how this iron powder visually maps things out. It completely proves a core concept in physics, which is Gauss's law for magnetic fields. If you just track the pattern, you see the field lines always loop from one end to the other. They go from a source, which we call the North Pole, to a sink, which is the South Pole. And because these lines absolutely have to close in on themselves to form loops, it tells us something really profound about our universe. Magnetic monopoles, meaning an isolated North or South Pole just chilling on its own, simply do not exist. Now, you've probably wondered, well, what if I just take a bar magnet and snap it in half? You don't get one north magnet and one south magnet. Nope, you just get two smaller magnets, each with its very own north and south pole. And it goes all the way down. Even if you zoom in and literally break a magnet apart into its individual atoms, down to the electrons and nuclei, you still cannot isolate a single pole. The absolute simplest magnetic structure allowed by the universe's physics engine is a dipole. It's always a pair, a source and a sink. Moving right along to Section 2, the displacement current bridge, connecting electric and magnetic fields. This right here illustrates the absolute beautiful symmetry of physics. For a long time, scientists knew all about Faraday's law of induction, right? You change a magnetic field over time, and boom, you magically induce a perpendicular electric field. But James Clerk Maxwell realized that the universe really loves balance, so he introduced the symmetric counterpart, Maxwell's law of induction. This states that a changing electric field will in turn induce a magnetic field. It's like the two fields are locked in this endless, perfectly synchronized dance, constantly creating one another. But Maxwell had a pretty tricky problem to solve. Imagine a circuit with a charging capacitor, basically just two metal plates with a gap of completely empty space between them. Current flows through the wire, sure, but no actual electric charge jumps across that gap, and yet a magnetic field is still generated around that empty space. So to make the math work seamlessly across a vacuum, Maxwell introduced this brilliant concept called the displacement current. Now, it's actually a bit poorly named because nothing is literally being displaced, and it's definitely not a physical flow of real charge. It's actually a fictitious current that represents the changing electric flux between the plates. It acts as this clever mathematical bridge, allowing the concept of current continuity to survive across empty space. So, the really crucial takeaway here is that these four glowing rules lock together to form Maxwell's equations. You can think of them as the complete control panel for the universe. They summarize the entire foundation of electromagnetism, from relating electric fields to charges, confirming there are absolutely no magnetic monopoles, to describing how changing fields induce one another. I mean, these four lines of math dictate the whole shebang, from how your compass points north, to how your phone connects to Wi-Fi, to how visible light travels across the cosmos. Okay, zooming way into Section 3, the quantum magnetism engine, electrons and magnetic moments. Every single electron in the universe is basically a microscopic magnetic engine, and they have two really vital properties. First up is an intrinsic property called spin, angular momentum. This spin generates a spin magnetic dipole moment, which is quantized simply as spin up or spin down. But here is the wild part. The electrons don't literally spin like tiny toy tops. I know the name is misleading, but it's purely a quantum property. Second, electrons in an atom possess orbital angular momentum, based on how they're arranged around the nucleus. And again, they aren't actually orbiting like planets around a sun, it's a quantum state. Ultimately, both this intrinsic spin and this orbital momentum combine vectorially to give you a net magnetic field. Let's scale our sensors back up to the material level for Section 4, classifying magnetic materials, diamagnetism, paramagnetism, and ferromagnetism. Depending on how all those atomic magnetic dipole moments interact with each other, materials fall into three distinct buckets. First, we have diamagnetism, and this actually exists in all common materials. It's a very weak repulsion from a magnetic field, but it's so incredibly feeble that it's usually masked by the other types. Second is paramagnetism. Here, atoms have permanent moments, but they're completely randomized until an external field forces them to temporarily line up, which causes a weak attraction. And finally, the rock stars, ferromagnetism. These are the strong, permanent magnets we all know, like iron or your everyday refrigerator magnets. In these materials, this special quantum effect called exchange coupling actually forces the electron spins of neighboring atoms to permanently lock into alignment with one another. Which brings us nicely to Section 5, Domains and Hysteresis, the making of a permanent magnet. So if iron naturally wants to align its atoms, why isn't every random piece of iron a permanent magnet? Well, naturally, iron is broken up into these microscopic regions called domains. Inside each individual domain, the atoms are perfectly aligned, but the domains themselves, they point in totally random directions, essentially canceling each other out. However, if you apply a really strong external magnetic field, the domains that match the field actually start to grow, shifting their boundaries and consuming the unaligned ones. And here's where the magic happens, hysteresis. When you take that external field away, the domains don't just snap back to random, they stay partially aligned, forever changed by their history. That persistent, leftover alignment is exactly how a permanent magnet is born. But wait, our HUD is throwing a critical thermal warning right now. Heat is the ultimate enemy of order. If you heat a piece of iron up to exactly 1043 Kelvin, which is known as its Curie temperature, the intense thermal agitation simply overwhelms that delicate quantum exchange coupling. The atoms are shaking too violently to hold hands, the domains totally shatter, and the iron suddenly loses its permanent ferromagnetism. It just reverts to being a weak, temporary paramagnetic material. Finally, let's pull all the way back to planetary scale for Section 6, Earth, the giant dipole, planetary magnetism. It is just incredibly elegant when you realize that the exact same fundamental Gauss dipole rule governing microscopic quantum electrons and scattered iron filings also dictates the behavior of entire celestial bodies. Our very own Earth acts as a massive magnetic shield, guarding our atmosphere from damaging solar wind. It operates exactly like a gigantic magnetic dipole straddling the planet's core. The physical laws just scale up perfectly from the subatomic to the planetary. So we've successfully scanned reality from the intrinsic quantum spin of an electron all the way up to the invisible magnetic shields guarding our planet. And through all of it, Maxwell's equations stand absolutely firm as the ultimate rulebook. But it does leave us with one final, pretty provocative question. We know Gauss's law states monopoles don't exist here. But with a universe so unbelievably vast, could there ever be some extreme cosmic condition out there, maybe at the edge of a black hole or dating back to the very birth of the universe, where a solomagnetic monopole actually breaks Maxwell's absolute rules? I'll let you ponder that the next time you look around and think about the invisible magnetic fields surrounding you right now. Thanks for joining me on this explainer, and keep questioning the blueprint.